Hi. In this video, I'm going to talk about fields because I think that is really important going forward. And we can talk about more example of vector space if we know what is a general field. Okay, so I will start with the definition of field. So a field denoted by F is a set on which in which two operation, just like in vector space we have this plus and dot. Here we have these two symbols plus and dot, but this time this the axiom that it the axiom that it follows is little different. Plus is same as like before, like here it is from F cross F to F, which means it takes two element of F and then gives back an element of F. And dot is just is from R, not R. This is from F cross F to F. Earlier, if you recall, in vector space, this dot was from, let's say, R. If we are defining vector space over R, then this was how it was defined: R cross V to V, right? So this thing was different from V. Okay, here these two are same. F cross F to F. Earlier it was R cross V. V is different from R, can be R, anything else. Okay, V. Okay, so the thing is here in vector space we needed the help of R. In place of R, I told you that in lecture 1 we could have any field. Okay, we will shortly seen after defining field concept of field that R is an example of field. Instead of R, we can have complex numbers. We can have any other fields like rational number, field of rational number, and we can define vector space over that also, right? So I will define it shortly. What it means to be a vector space over field. Okay, any general field, not over R, like any other field also. So before that, we need to know what is a field. So stay tuned for that. So these are the axiom, like A plus B is equal to B plus A. This one, and A dot B is equal to B dot A. Okay, A plus B plus C is equal to A plus B plus C, and A dot B dot C is equal to A dot B dot C. And now there exist different elements 0 and 1 in F such that this thing holds, like what is this thing? 0 plus A is equal to A, and 1 dot A is equal to A. 4 each element A in F in each non-zero element B in F, there exist C and D in F such that A plus C is equal to 0 and B dot D equal to 1. Okay. A dot B plus C is equal to A dot B plus A dot C. The elements x plus y and x dot y are called the sum and product respectively of x and y. Okay. Now I will take some example. Okay. Let's see. This example, this is very common, like this one, R. Okay. So, with how will you take the addition? I will take the addition as A plus B, B, like same as we define it, addition of real numbers. Okay. So like you see, plus 2, 2 plus, it takes two element 2 and 3 and it gives back 5, let's say. Similarly 5 plus 7, 12, right? And you check that this holds trivially, right? A plus B is equal to B plus A. Okay. A plus B plus C is equal to A plus B plus C. Like if you add something, then add this one, A, and if you add A plus B and then add C, this won't make a difference. Okay. With this addition, okay. And now let's say you can take 0 as 0, and so if you add 0 to something, it will be this one. Okay. And this is also same. Okay. Now A plus C is equal to 0. You can take, let's say, 2, and minus 2 will satisfy that purpose. Like every element has inverse. Let's say if you take any non-zero number, then we can take 1 by, let's say, 2, and then 1 by 2 will give 1. Okay. And this also satisfies, so you can check that. Okay. So let's take some non-trivial examples of field, and then you will realize it. Okay. Let's say example is Q, rational numbers. Okay, this also is a example of field. Okay, you can add two rational numbers. Okay, you can okay, you can do the same thing with same addition and same multiplication. This is also a rational field. Okay, and now let's take some example which is not a field. Okay, let's say this one is a field. You can check this. And now let's say this one, example, integers. Okay, so this one fails to be a field with like the standard addition. Like if you define addition to be this one, the normal one. Okay, and multiplication as defined, like standardly defined. Okay, why? Because for every non-zero number, let's say 2, 1 by 2 is the inverse, but 1 by 2 doesn't belong to Z. Like this is not an integer. So this one fails, right? Fourth one fails. Okay. So I think that will do the job for why it is not a field. And let's take another example. 4. This time uh, I will take let's say y this thing, this field Z4, to show that addition doesn't need to be like this normal addition, 2 plus 3 is equal to 5. Okay. Let's see this one. This is something denoted by Z5. Okay. So what is this? This has 4 element 0, 1, 2, 3, 4, and we denote it like this. Okay. So what we do is 0 plus 1 is defined to be 1. Like addition is defined to be this plus this standard addition, and then you take the remainder after dividing by 5. Okay. Okay. So what do we do? Let's say 0 plus 1 is 1, and then if you divide by 5, remainder is 1. So let's say 3 plus 4. What will it give you? 7, right? 7, and then remainder 7. When you divide by 5, you will get remainder equal to 2. So 2 is your answer. Okay. So this is my definition of field, like addition, field addition. Okay. So let's take another. Let's say 2 plus 4. This one is 6, and this is equal to 6, and divided by 5, it will be 1. Okay. So this is our actually addition. Okay. So I have demonstrated what is my definition of addition. Okay. Now multiplication, same way I define. You multiply, then remainder, find the remainder when divided by 5. Whatever is the remainder, that is the answer. Okay. So this multiplication is defined like this. Like let's say 1 into 1. This is 1, and after dividing by 5, you get 1. Okay. So 3 into, let's say, 4, you will get 3 into 4 is like 12, and divided by 5, you will get 3 into 4 is equal to 12, divided by 5, and remainder it will be 2. Okay. 12, so remainder is 2. Okay, and let's say 2 into 3. This will be 6, so remainder will be 1, dividing by 5. Okay. So you see that when you add two number, your remainder is always when you divide by 5, right? So you will get always a number between 0 to 4. Okay. Let's say something like if you okay. So that's why this definition makes sense, because when you are like this thing I want to highlight. Where is this highlighter? When you add two, like numbers from Z5, you get back a number in F, like Z5, right? Because if you add 3 plus 4, if it was regular definition, would have got 7, but instead we got 2, which is inside this set. Okay. So we get back a number in F only. Similarly, if you like multiply two number, you will get a number which is like inside this F, inside this. Okay. In this definition, at least 3, 4, you will get 2 instead of 12. So that's why here the addition and this scalar multiplication, this is good. Okay. And now what I want to say is like this thing also holds true, right? Just let me check this for you. Like, let's say a plus b. This is b plus a, and this is also 2, right? You take any 2 plus 3. This will be 6, right? You take this remainder when dividing by 5, you will get 1 only, right? Even if it's 3 plus 2. Sorry, what I'm saying. I meant 2 plus 4. This is 4 plus 2. This both are same, right? You will get 1 only. Okay. So similar. So that's why we say a plus b is equal to b plus a. Okay. This thing is first one. Okay. And next thing we need to check is, so this thing I verified. So our plus definition makes sense, right? So what is this bar? Bar we are like denoting is like a plus b. When you add this, you get a plus b bar. Like when you add addition is in this sense, this definition, like this definition. Here our addition is not the normal addition, right? So this is the resultant. Okay. So we need to verify this is equal to this, and similarly we need to verify this is equal to this. Okay, and this is also same. Like if you multiply AB, BA, this both are same. Like so, if you take the remainder from after dividing by 5, this is also same. Okay, so you can check that Z5 is actually a field. So how actually we find the remainder? Let's see. 2 into 2 has a remainder that is, sorry, 2 into 3 is multiplicative inverse. How do you find it? 2 dot 3 is equal to 6. So this is equal to 1 remainder, right? So this 3 is inverse of 2. And similarly, let's say I want to find inverse of 1. Then 1 is the multiplicative inverse because 1, 1 is 1. Okay, now let's say 3. What is its inverse? 3 into 1 will not work. 3 into 2 will not work. I think 3 into 2 will work. Okay, because it's 6. Okay, 4 into 1 equal to 4. So this thing will work. This won't work. Sorry. 4 2 is 8, and then 4 3 is 12. 4 4 just 16. Okay, 4 4 16, and 16 remainder 5 will be 1, and then there is no 5, right? So these are all the non-zero numbers. So this thing, 1 2 3 4, everyone has an inverse. This thing takes care of this one, right? This axiom that each non-zero element B in F has like D such that B dot D is equal to 1. Okay. Similarly, this thing also you can check additive inverse. This C is called additive inverse. Okay. So you can check these axioms also, that like 2 minus 2 is equal to 0, and 3 minus 3, sorry, 2 minus 2, not, sorry, 2 plus 3 bar is equal to 5, right? 1 bar plus 4 bar is equal to 0. 0 plus 0 is equal to 0. This thing. And 3 plus 2 bar is equal to 0. This is also 2. And 4 plus 1 is equal to 0. So every element has an inverse as predicted by this this fourth. Okay. And I also showed inverse of some element, right? Like this one, multiplicative inverse. And what do we need? And this also you can check, right? A plus 0 will be 0, and 1 into A is 0, like A, right? because 1 into 3 is 3, and let's say remainder by 5, it will be 3 again, right? And this one you can also check. So we have proven that Z5 is a field. Okay. So this is another example of a field. Okay. Okay. Now keep this in mind, right? This will be, we will use this in later videos. Okay. So already I've defined vector space over R. So in general, you can do, what you can do is like you can define vector space over field, and the modification that we need is just this one, over F. And the modification we that we need, instead of R, this is F. Okay. And any other thing, let's check here. This one is from F. One is the one that belongs to F, identity of F. Okay. So this does not necessarily mean that one is the real number. Okay, one is from field, any field. So I will give you an example softly. Just wait. Now each element x in V. This is from instead of R, you can talk about field over field. This space over field, and this is also over field. Okay. So this takes care of vector space over field. Okay. Let's just give an example, quick example, and then we will stop this video. Okay. Example of vector space over a general field F. Okay. In this example, I will take F to be Z5. Okay. Okay. So this one Z5 V is equal Z5 is a vector space over Z5. Let me just quickly change this. Mn, I will take M3 Z5. Okay. So how it is a vector space? Check this. M3 denotes the matrix, okay, with element from Z5. Let's take it. Okay, okay. So 3 by 3 cross matrix. So I can, what are element of Z5? This one, right? 0, 1, 2, 3, 4. I discussed this, right? Here. These are the element, okay? Z5. So you can take any element from there, okay, and fill this. Let's say this matrix, okay? And let's take this matrix. Okay. Now if you add this, you will see 0, 0, 0, 1, 1, 2, 3, 1, 4. Okay. 4, 1, 5, 2, 1, 3, 3, 1, 4, 3, 0, and 2, 1, 3, 3, 1, 4, 0, 2, 4, and 5, 3, 4, 3, 3, 4. Okay. So you can see that This one looks okay. I have made an error. This one, instead of 5, you should write 0 because we are in Z5. So can you see the difference? If it was a general matrix over R, then this would have been 5. This should have been 5. But we are working in Z5. Okay, so remainder will be 0. Okay, and let's give you the like multiplication. So dot, and dot will be from as I told earlier, this will be from Z5 to Z5. Okay, so let's take 1 bar and multiply with this matrix. 6 cannot be there, right? 4, 2, 3, 1, 2, and in a random matrix. Okay, so you check this that this will be this only, right? Because we are multiplying with 1. And and let's do another one. 2 into this 4 plus 5, not 5, let's say 2 bar, 3 bar, 1 bar, 2 bar, 3 bar, 2 bar, 4 bar, 2 bar. Okay. So 8, and then remainder by 3 will be 8, 3. Okay, 2, 2, 4, 2, 2, 6, 1, 2, 1, 2, 4, 6, 1, 2, 4, 8, 3, 2, 2, 4. This one. Okay. So you can see earlier when we were doing R vector space like M3R over R, this vector space over we defined 2 into this matrix 4, 2, 3, 1, 2, 3, 2, 4, 2. This will be 8, 4. This one is 6. This one 2, 1, 2, 2, 4, 6, 4, 8, 4. Can you see the difference? We are getting different things, right? So that's I think it for this vector space, and we will meet again on like next lecture. Okay, that's it for today.